Hello everyone, in this lecture, I'm going to show to you how to derive the mean, the variance, and the moments of Weibull distribution. Weibull distribution is a continuous probability distribution with a probability density function or PDF shown in here. Now let's start with our derivation of mean. Mean is equal to expectation of x, and since this is a continuous probability distribution, it is equal to the integral of x from here times the probability density function, which is this one, dx. This x is from 0 to infinity, so we have here 0 to infinity. Then let us move the constant outside of this integral, so we have this one. Then integral of, for x, let us combine both x, this one and this one. So we have here gamma minus 1 plus 1 is gamma, so we have here gamma. Then the rest of the terms, e raised to negative x raised to gamma over beta dx. This is from 0 to infinity. Now to simplify this integral expression, we need the use of the gamma function, which is defined to be integral of t raised to alpha minus 1 e raised to negative t dt from 0 to infinity. Now, in order to simplify this one using this, we need to make them similar first. Now, for the exponential terms, let this t be equal to this one, x raised to gamma over beta. So we have here let t is equal to x raised to gamma over beta. Then from here, we have x is equal to beta t raised to 1 over gamma. Then dx will be the derivative of this one, which is 1 over gamma beta t 1 over gamma minus 1 times the derivative of beta t, which is beta, and then dt. Then let us substitute this in here. So we'll get for the mean, so we have here gamma over beta, then integral of, for x, let us use this. Then since this is raised to gamma, so we have here times gamma. Then e raised to negative. For this one, which is this one, let us use t. Then for dx, let us use this. So we have here 1 over gamma. Now for the limits, since this is in terms of t while this one is in terms of x, now if x is 0, in here 0 raised to constant, which is greater than 0, still 0, and 0 divided by a constant, which is greater than 0, still 0. So we have here t is 0. Then if x is infinity, in here infinity raised to constant, which is greater than 0, still infinity, and infinity divided by a constant, which is greater than 0, still infinity. For the constant gamma, we can cancel this one and this one. Let us combine all the betas. So we have here negative 1. Then from here, we can cancel out this gamma and gamma. Then we have here beta raised to 1, so we have plus 1. Then in here, beta raised to 1 over gamma minus 1, so we have here plus 1 over gamma minus 1. Then in here, plus 1. Then we can cancel this negative 1, plus 1, and minus 1 and plus 1. Then integral of, now let us combine both these from here. So we have here t raised to 1 plus this one, which is 1 over gamma minus 1. Then e raised to negative t, then dt. This is from 0 to infinity. Then we can cancel out this 1 and minus 1. So we left with, for this one, we have beta raised to 1 over gamma, then integral of t raised to 1 over gamma, then e raised to negative t dt from 0 to infinity. Now, if we compare this one with our gamma function, they are still not the same because this is alpha minus 1 while this one is 1 over gamma. So let this alpha minus 1 to be equal to this 1 over gamma. Then from here, alpha is equal to 1 plus 1 over gamma. Then from here, in here, alpha should be greater than 0. Then in here, since gamma is greater than 0, so we have here greater than 0 also. So alpha is greater than 1 or greater than 0. So this one is satisfied. So it's okay to have this kind of transformation. Then using this in here, we'll get beta raised to 1 over gamma integral of t raised to alpha minus 1 e raised to negative t dt from 0 to infinity. Then now this integral expression is same with our gamma functions. Then we can replace this one by big gamma of alpha, which is from here. Then using this in here, we'll get beta raised to 1 over gamma times this one, big gamma of 1 plus 1 over gamma. So now this is our mean for the Weibull distribution. Now let's proceed with our derivation of variance. Variance originally has the formula expectation of x minus expectation of x. This is squared. Then we have another formula for variance, which is expectation of x squared minus the square of expectation of x. Now this one is derivable from here, and we're gonna use this one for our derivation. Now for the expectation of x, it is same with the mean, so we have derived it to be this one. So we can use this one in here. Then for the expectation of x squared, we haven't derived it yet, so we need to derive this one first before we can derive our variance. So expectation of x squared. Since this is a continuous probability distribution, it is equal to the integral of x squared from here times the probability density function, which is this one, then dx. This x is from 0 to infinity, so we have here 0 to infinity. Then let us move the constant outside of this integral. So we have gamma over beta, then integral of, let us combine both x, this one and this one. So we have x raised to gamma minus 1 plus 2 is gamma plus 1, so we have here gamma plus 1. Then the rest of the terms in here, e raised to negative x raised to gamma over beta dx from 0 to infinity. Now, similar to what we have done in our derivation of mean, we can simplify this integral expression using the gamma function, which is defined to be integral of t raised to alpha minus 1 e raised to negative t dt from 0 to infinity. Let this t be equal to this one. We have let t is equal to x raised to gamma over beta. Then from here, x is equal to beta t raised to 1 over gamma. Then dx will be 1 over gamma beta t raised to 1 over gamma minus 1, then beta dt. Then let us substitute this in here. So we'll get expectation of x squared is equal to this one, gamma over beta. Then integral of, for x, let us use this one. We have beta t raised to 1 over gamma times this one. We have gamma plus 1. Then e raised to negative. For this one, x raised to gamma over beta, which is this one, so we can use this t in here. Then for the x, let us use this in here. Then beta t raised to 1 over gamma minus 1 beta dt. Then for the limits, if x is 0 in here, 0 raised to constant, which is greater than 0 is still 0, and 0 divided by a constant, which is greater than 0 is still 0. So we have here t is 0 when x is 0. Then if x is infinity, we have here infinity raised to constant, which is greater than 0, still infinity, and infinity divided by constant, which is greater than 0, still infinity. So we have here infinity. Then we can cancel out this gamma in here and gamma in here. Then we can combine all the betas from here. So we'll get beta raised to, for this one we have negative 1. Then in here we have plus 1 over gamma times gamma plus 1 is 1 plus 1 over gamma. Then in here plus 1 over gamma minus 1, then plus 1. Then integral of, for t, let us combine both these in here. So we'll get t raised to, for this one, 1 over gamma times gamma plus 1 is 1 plus 1 over gamma. Then from here, we have plus 1 over gamma minus 1. Then e raised to negative t dt from 0 to infinity. Then we can cancel out this negative 1 and plus 1, minus 1 plus 1. In here, 1 and minus 1. Then it is equal to 1 over gamma plus 1 over gamma is 2 over gamma. So we have here beta raised to 2 over gamma. Then integral of t raised to 1 over gamma plus 1 over gamma is 2 over gamma. Then e raised to negative t dt, which is from here. Then this is from 0 to infinity. Now, if we compare this one with our gamma function, they are still not the same because this is alpha minus 1 while this one is 2 over gamma. So let this alpha minus 1 be equal to this 2 over gamma. Then from here, alpha is 1 plus 2 over gamma. Then since gamma is greater than 0 in here, this alpha is greater than 1 or greater than 0. So we satisfy the condition in here, which is this alpha in here should be greater than 0. Then using this one in here, we'll get beta raised to 2 over gamma integral of t raised to alpha minus 1 from here, then e raised to negative t dt from 0 to infinity. So now this gamma function is same with this one. So this one is big gamma of alpha, which is this one. Then from here, we can use this one in place of alpha. So we have here beta raised to 2 over gamma times the big gamma of, for alpha, let us use this one, 1 plus 2 over gamma. So this is our expectation of x squared. Then for our variance, we have this formula. Let me rewrite that one in here. Expectation of x squared minus square of expectation of x. Then it is equal to, for this one we have this one, then minus the square of expectation of x, which is this one, and this is squared. Then let us distribute this one for its term in here. So we'll get beta raised to 2 over gamma. Then this is big gamma squared of 1 plus 1 over gamma. Then we can factor out this expression by the common term beta raised to 2 over gamma. Then minus big gamma squared So now we have our variance for the Weibull distribution. Now let's proceed with our derivation of moments. Moments is expectation of x raised to n. And since this is a continuous probability distribution, it is equal to the integral of x raised to n from here times the probability density function, which is this one, dx. dx is from 0 to infinity, so we have here 0 to infinity. Now, we can move this constant outside of this integral, so we have here gamma over beta times the integral of, we can combine both x, this one and this one, so we have here x raised to n plus gamma minus 1. Then the rest of the terms, this in here, dx from 0 to infinity. Then, similar to what we have done in our derivation of mean and variance, we need the use of the gamma function, which is defined to be integral of t raised to alpha minus 1 e raised to negative t dt from 0 to infinity. Then we need to make them similar in order to simplify this one. So let this t be equal to x raised to gamma over beta. So we have here then from here x is equal to beta t raised to 1 over gamma. Then dx will be the derivative of this one, which is 1 over gamma times beta t raised to 1 over gamma minus 1, then beta dt. Then let us substitute this in here, so we'll get gamma over beta from here times the integral of, for x let us use this, then this x is raised to n plus gamma minus 1, so we need to multiply this 1 over gamma by n plus gamma minus 1. Then from here we have e raised to negative 4x raised to gamma over beta, which is same with this one. We can use this t. Then for dx, let us use this. One over gamma minus 1 beta dt. Then for the limits, if x is 0, in here we have 0 raised to constant, which is greater than 0 still 0, and 0 divided by constant, which is greater than 0 still 0. So we have here t is 0 when x is 0. Then if x is infinity, in here we have infinity raised to constant, which is greater than 0 still infinity, and infinity divided by constant, which is greater than 0 still infinity. So we have here t is infinity when x is infinity. Then we can cancel this gamma in here and gamma in here. Then let us collect betas. So for the betas inside this integral, let us move them out. So we have here beta raised to, for this one we have negative 1. Then for this one, beta raised to this. So we have here 1 over gamma times n plus gamma minus 1 is plus n over gamma plus 1, then minus 1 over gamma. Then the beta in here, we have plus 1 over gamma minus 1. Then from here we have plus 1. Then integral of, let us combine this, we have t raised to, in here we have 1 over gamma times n plus gamma minus 1, so we have here n over gamma plus 1 minus 1 over gamma. Then from here we have t raised to 1 over gamma minus 1, so we have here 1 over gamma minus 1. Then e raised to negative t, then dt from 0 to infinity. Then we can cancel out this negative 1 and plus 1, this 1 over gamma and plus 1 over gamma, this minus 1 and plus 1, this plus 1 and minus 1, this minus 1 over gamma and plus 1 over gamma. So we're left with beta raised to n over gamma from here, then integral of t raised to n over gamma, then e raised to negative t dt from 0 to infinity. Then if we compare this one with our gamma function, they are still not the same because this is alpha minus 1 while this one is n over gamma. So let this alpha minus 1 to be equal to this n over gamma. So we have here, let alpha minus 1 be equal to n over gamma, then alpha will be equal to 1 plus n over gamma. Now this gamma function has a restriction. This alpha should be greater than 0. So from here, gamma is greater than 0. So alpha will be greater than 1 or greater than 0. From that argument, this is satisfied, so it's okay to make this transformation. So then let us use this in here. So we'll have beta raised to n over gamma, then integral of t raised to alpha minus 1 from here, then e raised to negative t dt from 0 to infinity. Then if we compare again this one with our gamma function, they are now the same. So we can replace this one by big gamma of alpha from here. So we have here big gamma of alpha. Then we can use this in place of alpha in here. So we'll have beta raised to n over gamma from here times big gamma of this one, 1 plus n over gamma. So this is expectation of x raised to n from here. So now we have our moments for the Weibull distribution.